So thank you for the organizers for putting up this very nice program and squeezing us in. So this is joint work with Juha Tolvanen, who is a colleague of mine, and Alexander Wagner, who is in Salzburg, and it fits on this strategic component of artificial intelligence. Well, for this audience, I don't think I have to spend, again, much time on applications of algorithmic systems, but really here just point out the fact that in most or in many of these occasions still, it is the case that humans retain the final decision power and machines provide advice, recommendations, etc. So in our work, kind of at a high level, and the literature has kind of tried to analyze the question of where, to what extent humans or machines should make the final decision. And this is the question, if you frame it in the theory of the firm, you could ask, the human retains some formal power, and maybe the machine has what's called real power in this literature. And so the question of whether the human should retain this formal last decision power has always, a trade-off here, and the literature has pointed out to benefits and costs. So on the benefit sides, we have the fact that, as pointed out, especially in the banking industry and the finance industry, humans have some additional soft information that is not easily available to the algorithm. For instance, they may know something about the firm that is hard to codify. Humans may be able to correct some bias that the algorithm has, depends on the type of decision. Or in general, we and regulators are kind of reluctant, more generally, to artificial intelligence decision and errors. We are really intolerant to mistakes by machines, so having the human make the last decision kind of softens that blow. On the cost side, of course, as already Xavier pointed out before, of course, these humans, of course, anybody who's ever gone to a behavioral economics talk would know that humans are not very good decision makers. We have lots of biases, stereotypes, errors, and most importantly for what we're going to do here, human decisions will typically be slow and costly compared with machines. Okay, so in this paper we try to investigate this trade-off with a specific setting, okay, which is in the context of hotel pricing. For a sample of hotels in Central Europe. In this setting, hoteliers will receive price recommendations by an external consulting company and will retain the final decision. Okay, will retain the final decision. They have to update prices manually if the price is going to be changed. We will show or try to show that actually there is going to be substantial inertia. Managers are going to be much slower in adjust than machines. This is going to generate some conflict of interest between the machine who wants frequent adjustment and the humans who are rather slow. We're going to have a simple model that generates pattern consistent with the data. We're trying to take the model to the data to kind of, at the end of the day, ask whether delegation would improve things, and under kind of first whether kind of understand the kind of the parameters of the model in terms of, for instance, whether humans do have more or less information that may be relevant, and finally to perform this counterfactual of delegation. Okay, so very briefly on the literature, I think we bring a little bit this literature of advice into the fore here for this whole literature of artificial intelligence that very often treats both recommendations and decisions in a very similar way as the output, because this is the machine output, but it's very different, as we know from information economics, it's very different to think of advice than to think about decision making, and the whole problem of advice has attracted attention for the last 40 years to economic theory. So we are kind of following that literature. In particular, we have our model will be quite close to work by Navin Karthik, Ottaviani, and Squintani. But I mean, the main ideas are common to the literature of advice. There are very brief applications to AI, mostly theoretical and really just pointing out the potential use. And we think we contribute also to the the standard literature on, that is emerging on humans as evaluators, because often in that literature, the counterfactual is the introduction of some, often going to be a recommendation system. And we highlight the potential conflicts of interest that may arise in this type of recommendations, in which the machine may have eventually will eventually learn to optimize something different from what the human is doing, and it's going to lead to some potential bias in communication, as we try to show here. Okay, if there are no questions on the motivation, the data we have, I'm going to spend some time kind of showing some descriptive statistics so that you see more or less what we talked, then I will explain the model. So this is data from a revenue management consultancy that provides recommendation for something like 200 prices in Central Europe. We will observe for each of these hotels, or for a whole year, almost a year, we will observe their prices every day for every type of room, okay? And we will also serve the recommendation that the consulting company gave to this manager on that particular date, okay? And they may be the same or may be different depending on the specifics. Because we have for every room type, for every date of arrival, for instance, we arrived to Rennes today, we have a night in a hotel, you could have booked in every previous day. This gives you quite a rich panel of like 5 million observations. But of course, not every day prices change for these hotels, so prices are quite sticky relatively to these 5 million. We see something like 130,000 price changes, but recommendation changes much more frequently. Roughly, recommendations change every week, while prices change every month. The first observation that we have is that the recommendation, and we have shown in previous work also, has a causal impact on the action, the decision of the manager, directly on the probability of an update. So what we have here on the x-axis is the change in percentage points in the recommendation since the last update of the manager, and on the y-axis we have the probability that on a specific day, on a random day, the manager actually makes an update on a particular room. So what you see here, first of all, is when the recommendation hasn't changed, the probability that there is a change by the manager is negligible, it's below 1%. Okay, so that means on average they would take 120 days or 4 months to make a price change. So it's a very sticky process. On the other hand, once the recommendation has changed, that attracts attention for the manager, and you see that the probability of a price update is substantial, but it's still, between 10 and 20% for the majority of observations, which is rather low compared with the algorithm, which is changing much more frequently. So in this setting, these recommendations have a substantial impact, not only because they may lead the manager to change their decision, but also because they may actually, it turns out to be easy in their environment to accept a recommendation. So accepting recommendations for the managers are easier than, say, changing the price to some other price that is not exactly the recommended price. For instance, if the current price is 100 and the recommendation is 110, the manager can, with one click, directly implement that new price. But if he wants to charge set a price of, say, 108, he needs to kind of go into another screen. He will acquire, or she will acquire some further information, and then will make this final decision. So it's kind of a more costly process. So recommendations here have some effective direct influence on prices because they are kind of easier to implement than other prices. They are not just cheap talk. No, we don't know that. So we are just going to assume for the most of the paper, so maybe we can discuss this later, but we will take two approaches. One approach is let's see what managers do, and let's take the recommendation completely as a black box. Okay. The other one is, let's assume that the recommendation actually maximizes what the consulting company tells us they should be maximizing, which is the same exact profit function that the hotelier has. And in the second case, the only conflict of interest will be that definitely the machine does not internalize the costs of the manager to make these decisions. Okay, so these are the two. Both of them give very similar influence, results, sorry. So, right, so we don't know what the algorithm is doing in a sense. That's all we see is the output. We don't see any of the, what's going on in there. Yeah. And so this is going to lead to some sort of bracketed decision making where the manager is going to first decide whether to put attention to a price. If she puts attention, he's going to kind of decide whether to accept the recommendation or acquire more information. And in the last stage, if he acquires further information or she will actually choose the price that she finds optimal given her information and the recommendation. So what the first thing to notice is that actually recommendations are extremely influential. So 90 to 95% of the price changes coincide with a recommendation. Okay, so 95% is this is conditional on the recommendation having changed. So when the recommendation has not changed, of course, it cannot match. So on average, the number is like 90%. So 10% of the price changes are manual, and 90% are copying the recommendation. And importantly, or surprisingly to us, this slope is actually positive, and this is robust, meaning the higher the change in the recommendation since the last update, the more likely it is that the manager will actually accept it. And from people who, if you have some intuition for models of advice, you would typically expect the opposite, because as the recommendation becomes more exaggerated, it should be more, if there is a bias, this bias should be even larger. Okay, so it's a bit of a counterintuitive result. Now, we highlight moral hazard here as the friction in this setting because the hotels face costs from adjustment that the manager does not really, the algorithm does not really incorporate in its decision process. And so this gives the algorithm an incentive to indeed exaggerate information, right? Because it can lead the manager to update, whether exactly to match the recommendation or not is second order importance. For them, what is important is that the price is not sticky into something that was previously optimal but no longer. In equilibrium, of course, one could understand that the managers will have some understanding that the algorithm is biased. Not exact understanding maybe, but they will eventually learn. These are companies that have been working together for years, so we expect the manager to kind of gather the right signal from the, extracted from the recommendation. But what happens is that very often they will just copy because it's kind of easier, and so that's going to lead to still some bias in decision making. What is, in that sense, very similar to this work by Kartik, for those of you who know that paper. So there they have a model of chip talk in which some receivers were naive in the sense that they always chose the price, if you wish, that the recommendation gave them because they didn't know better, okay? The difference here is that the naivete, if you wish, we are going to think of it as endogenous because these are always the same decision makers. Sometimes we see them copying, sometimes we don't see them copying. It must be that there is some friction, some cost to kind of processing this information. So our model is going to be very similar to a model of Kartik with this model of Kartik, but endogenizing this naivete by making this adjustment cost actually effective. And so in that model, in those models in general, very briefly, we predict that when the manager actually acquires makes the effort to choose the price manually, it has to extract the signal which is less than 1-to-1 with the recommendation. So if the recommendation increased by 10, you would expect that the manager expects the actual signal of the algorithm to have increased by 6, by 7, etc. And this is exactly what happens in the data. So what you see here is the red line is the 45-degree line, and here you have the change both positive and negative, and this is just the linear fit, but roughly speaking, things are symmetric with a slight blip around 0, which means that, and the slope is substantially lower than the 45-degree line, which means that a 1% increase in the price, indeed, conditional on the manager going all the way to change the price manually, would lead to an increase in the price of 60 to 70%, 60 or 70 cents of a euro, which is consistent with the manager understanding that the algorithm has a bias. Okay? But remember, although the algorithm has a bias, the manager copies in a very high percent of the cases their recommendation. It passes it through exactly. And this kind of is a substantial conflict that arises here that suggests that the strategic component of recommendations is harming here decision making. So very briefly, to kind of understand to what extent the different sources contribute to, if you want, mispricing here, we have a simple static model in which hoteliers ideally would charge a price, wants to charge a price P, and ideally they have a loss function when the price departs from the ideal price P star. We allow P star to have three components: X, which is observed by the recommendation algorithm only; Y, which is observed by the manager upon putting attention to the price. These are things that the manager will know just because she is in the business of running this hotel, presumably will know things about, costs or demand that maybe the algorithm doesn't know. And Z is actually what you will learn if you really put attention to it. If you really go all the way, look at prices of competitors, for instance, which are available in their dashboard, or look at previous bookings, etc. We assume for the model that they are all IID, and for this presentation that they are normal. What is key in the model is we are going to take a very simple stance on how the recommendation is designed. We are going to assume that it's just going to be some linear function of the signal. Okay, we play with this. We are going to actually show empirically that this is an epsilon equilibrium, but we are not going to allow for very complicated functional forms here, so we are going to just simply say that if the recommendation increases by 1%, you can extract indeed a linear, say, when lambda is 1, you would extract a 1% increase in the price, but if the lambda is less than 1, you would extract actually a lower than 1% increase in the signal that the algorithm has. The hotelier will observe the recommendation, doesn't observe X, which is information, but just observes the report, R, and chooses whether to remain inactive, that is, set the same price as before, or put some attention. If you put some attention, you need to pay a cost C1. If the hotelier then puts attention, then she observes Y, which is the information that she can gather on her own, and then decide whether to charge P equals R or acquire further information. Okay? P equals R, at this stage, you cannot set a price. Optimally, you can only set the recommendation or nothing. And then if you acquire further information, then you observe Z a further cost C2, and these costs are correlated. So we think of these two costs as attention. And so within a particular day for a particular hotelier, you would expect that the cost of putting attention to a price or acquiring further information are kind of linear to each other. We're going to assume that. And in this latter case, she's going to choose P equals to what she believes is the ideal price. That's the expectation of X given R plus Y plus C. Okay? I don't probably have much time to go into the model, but just briefly, what is the key mechanism in the model is that suppose that the recommendation is this blue point here, the manager immediately knows that the actual signal is her expectation of X given R, because in equilibrium kind of will know what this bias lambda is. That means that the interim distribution of her ideal price, namely X plus Y given R, is going to be centered on the expectation of X given R, but not on R, okay, because of the bias. These two numbers are different. And so her optimal choice of whether to accept the price or continue is going to be some inaction bands, but they are going to be centered at R and not at the mean of the distribution. So this is going to create a selection, okay? It's going to create selection because when the manager decides to optimally continue to acquire further information, it's going to be on average more likely that her information was kind of in the opposite direction than the recommendation. So that's going to mean that for our model is not going to be identified directly from just running a naive OLS regression like I did before in this picture, because this there is going to be selection bias if our model is true. Okay, so we need to use structural methods to identify lambda. That's what it says here. Then the manager is going to go back one stage and choose whether to put attention when the cost of inaction, which is the blue curve, is above either the loss of this red line, which is the loss if she actually moves on and puts attention. I don't know if I turned this on. There's going to be an inaction band outside this recommendation center. Okay, very quickly. As back to your question, the algorithm, we assume in the main part of the paper, we assume that it actually minimizes the same payoff function that the manager has, but does not take into account these costs of acquiring these C1 and C2 costs of making decisions. And we're going to assume that there is partial commitment in the sense the code is written for all prices, so they are not going to be written for specific values of X. So this is going to be chosen ex ante, but there's still going to be a Nash equilibrium in a sense played, because given the belief that you have about lambda, the algorithm may actually deviate slightly. Alternatively, we can estimate the whole model as a decision problem in which we just take lambda as a parameter, okay? We take lambda as the parameter of the model, so this is just in the mind of the hotelier, what is the bias that the algorithm has, okay, that allows us to better rationalize the data. Both estimations give similar results, so I'm going to stay with the game theoretic estimation. Okay, we have 7 targets, which are just based on the distributions of prices and recommendations. And again, we have these 2 possible explanation, kind of alternative estimation ideas, to take lambda as a parameter or as an output of the model. So this is with the pool data. We estimate everything for every hotel, but to summarize, we find that the distribution, the standard deviation of the information held by the algorithm is lower than the standard deviation of the information held by the manager. Okay, so we find that the manager has actually substantial, in a variance decomposition, it has actually substantial information compared with the algorithm. The algorithm is not so well informed. But actually, given that the manager copies so often and updates so infrequently, that means that the information that the manager must have is very expensive to use or to acquire. Okay, so we find that substantial costs, this depends on these are log normal distributions, but what matters is the relative B1 and B2. B1 measures relative cost of the mean of making a decision which is just copying, and you see is substantial compared with the standard deviations. And what is very, very large, and you almost never do, of course, is to go all the way and acquire full information, which is an order of magnitude more expensive in our model, because it seems that the manager, although it would depart very often from the recommendation, it doesn't almost do so. Why does this come out from the estimation? Well, because we see substantial dispersion in decisions from the managers when they actually do depart from the recommendation. They do not depart by a few cents, they actually depart by dozens of euros, okay, by a substantial amount, which suggests that when they don't do it is because they have high costs. And we estimate a lambda of 80%. Remember, lambda around 70% was the naive estimate. So 10%, so from 70 to 80% is just, the difference is the negative selection that the model incorporates. The model, this is with, of course, here I'm saying always estimation as a game, so you are not actually fitting this line perfectly. We are predicting a bit of more, overshooting a bit on the bias, perhaps, at least on the pool data, but we do better on the specific hotels. And the model can also predict this increasing pattern in the probability of copying, which is kind of counterintuitive, but here it comes from the combination of the bias plus the adjustment costs. The main question we started with is, would we want these companies to actually delegate decisions to this algorithm? Now in the industry, I will finish much earlier. So in the industry, there is a big debate there is apparently only one company that is fully delegating. There are a few companies that do partial delegation within some bands. Most of the companies are just doing recommendations because they do not want the liability, okay? And so the question is kind of why do they do this? Well, we find kind of a naive reason for it is indeed that the algorithm seems to be not sufficiently informed, or at least the managers perceive the information as much more valuable than the information held by the algorithms. We use a reveal preference approach, so we cannot really test whether this is true. We take them from the fact that they choose different prices that actually they disagree, okay? They have some information that the managers don't have. But in the industry, it seems to be this is their perception. In our case, the fact of the matter is you can still use our model to kind of try to say what would have been the profits of this company relative, okay? How much would be the mispricing loss after you actually delegate? And so in all hotels, we find that if you delegate, you have a substantial reduction in this mispricing loss between 7 and 25 percentage points. I mean, again, what exactly this is in dollars, hard to make a point, but still, in terms of how much we identify to be this mispricing loss is a substantial gain from the algorithm. Although the decisions are much less informed, they are much more frequent, they are much less costly, and they do not face this bias, okay? They are always unbiased. Now, we also compute the counterfactual when the manager thinks that the algorithm is biased, not because of the conflict of interest, but simply because he doesn't know what's going on, okay? So if that is the case, the hotel manager will actually underestimate the gains from delegation because doesn't understand that once we delegate, the algorithm will no longer be biased because the algorithm will no longer have to convince the human to make decisions. Now, it turns out that for some hotels, this makes very small difference because we identify small biases. For some hotels, it accounts for 20% of the gains, okay? Still, it's not a substantial change, turns out, because indeed the manager very often does pass on the information, which kind of puts a limit onto how bad this can be. Okay, so to conclude, we study algorithmic recommendations from the perspective of advice. Private information held by human managers, we find it to be very sizable. At least humans perceive themselves to be better informed than the algorithm, but does not translate into superior decisions because they are just costly and slow. Adjustment costs of inattention induce this conflict of interest, which we think at least that it is common to quite a few decision problems in which humans will have some sort of use the recommendation as the default option, okay, but may have a default option, and the algorithm may want to may both try to provide information, but also to motivate action or experimentation from the human. And taking this into consideration, we think it's important. In our setting, delegation is likely to improve outcomes, although of course the gains vary widely across hotels, especially some of them seem to have a better understanding of the market and therefore they gain less from delegation. Thank you.